we are going to learn about something called as term symbols. So term symbols is one of the topics in coordination chemistry, wherein we learn about atomic terms, microstate, degeneracy, etc. And also we have, once we know the atomic term symbols, we will also learn the molecular term symbols. So it is one of the most important concepts in coordination chemistry, and most of the questions in CSIR net are focused on term symbols if you can consider the previous year question papers. So before going into term symbols, the first thing that we will understand is about microstates. So there are three things that we will learn in this video. The first is microstates or degeneracy. The next is the atomic term, and then we will also learn about term symbols. Okay. So all three are three different things. So we have three parts. The first is microstates. The second is atomic term. And the third is term symbol. So we have to go step by step. First we will learn microstate, then atomic term, and then we will go for term symbol. So basically this microstate is basically the arrangement of electrons in a partially filled subshell. That is the actual definition of microstates. It's basically arrangement of electrons in a partially filled subshell, which means, see, when you consider any orbital, say for example P1. So this is a configuration, right? So now P1, basically we draw it like this. Okay, but this is called as an arrangement, okay, wherein we have put the electron in the first orbital, which is the orbitals are designated as +1, 0, -1. But then electrons, we know that they can occupy any space. Now since all are vacant, the electron can also be here, the electron can also be here, right? And also the electron can have either a spin of +½ or -½. So basically whenever we give a particular configuration of any molecule, the electrons in that particular configuration can be arranged in n number of ways. So that arrangement of electrons, so that is not possible in a fully filled subshell, right? Say for example I say P6, which means you have all these 6 electrons filled in all the 3 orbitals of P, which means there is no other possibility of filling. So this is the one and only arrangement that is possible. So whenever you have partially filled orbitals, then only we talk about this word called as microstate. In a fully filled orbital, we won't have this concept of microstates, or nor will the concept of degeneracy arise. Okay. So now what happens is this arrangement of electrons, so number of arrangements, how do we find out the number of arrangements of any partially filled orbital? For that we have a formula. So the formula is n factorial divided by r factorial into n minus r factorial. So this is the formula. So say for example for P1 I have drawn 3 different arrangements. So if you have to find out the number of possible arrangements for any particular this thing, you can use this formula. Now what does n denote? Here n denotes the maximum electrons that can be filled. For example, for S it is going to be 2, for P it is going to be 6, for D it is going to be 10, and for F it is going to be 14. So this is the maximum number of electrons that can be filled. Now R is equal to number of electrons that are occupied. In this case I have given you the number of electrons that are occupied as 1. So R value you will take it as 1, and N value you know that here 6 electrons can be accommodated because it's a p orbital. So this is a straightforward formula to find out the microstates. So for example, let us do an example. So we'll take the same example P1, and we'll check how many possibilities are there for the electrons to be filled. So there is only 1 electron, so I have given you only 3 possibility, but actually if you see, you will understand how many possibilities are there. Now you see n factorial. So in p orbital, maximum number of electrons that can be filled is 6 divided by r factorial. So r is the number of electrons that is present. So here only 1 electron is present. So you put up factorial here. So 6 factorial divided by 1 factorial into n minus r. So here 6 minus 1 factorial. So if you solve this, 6 factorial divided by 1 factorial into 5 factorial. No, so 6 factorial you can write it as 6 into 5 into 4 into 3 into 2, or the simpler way is 6 into 5 factorial you can write it as, and here you can write it as 5 into 1 factorial is 5 factorial. So this 5 factorial and this 5 factorial will be cancelled. So the correct answer is 6. So there are actually 6 possible ways of arranging this P1. As I told you, I have given only one possibility. So there can be other possibilities also. So totally there are 6 possibilities. I have given you all 3 spin up. Now the next possibility would be all 3 spin down, or 1 spin up, 1 spin down, like that. So total number of arrangements that is possible for a given configuration can be determined from this value called as microstates. All 3 spin up is one possibility, wherein you have 3. The second possibility is spin down. So basically this, now P1 is a very small configuration for which we can easily find out even by placing that now 3 and then 3. But every time you can't do this combinations and check, right? That is why we are using this factorial formula to determine the number of arrangements. Okay. So now let me do one more example for clarity. Now if I say I have a configuration P3, okay, I need to find out the number of microstates. That is basically the number of type of arrangement that are possible for this particular configuration. Now if you can see, this is not a fully filled configuration. Let us see how many microstates are available. So the formula is n factorial divided by r factorial into n minus r factorial. So we simply need to substitute. So p orbital, the maximum number of electrons that can be filled is 6. So n value is 6. R value is the number of electrons that are available. So here 3 electrons are available. So 3 factorial into 6 minus 3 factorial. So you can solve this. 6 factorial divided by 3 factorial into 6 minus 3 is again 3 factorial. So either you can fully put it and solve it, or the better way is up till the denominator part you can write it. So 6 into 5 into 4 into 3 factorial divided by 3 factorial into 3 factorial. So 1 3 factorial and 1 3 factorial will get cancelled, and then you can write it as 6 into 5 into 4 divided by 3 into 2 into 1. So 3 2s are 6, 2 2 gets cancelled, 5 4s are 20. So the correct answer is 20. So if you can see here, as the configuration, the number of electrons keeps increasing, the number of possibilities of arranging them is also increasing. That is why the formula becomes more important. So for P3, there is basically 20 different types of arrangements which you can place those 3 electrons in those given set of orbitals, and so the number of microstates here now becomes 20. Okay. Now sometimes we also get configurations like this. For example, you have a S1 P1 configuration. That is, there are 2 electrons. One electron is present in the S orbital, the other electron is present in the p orbital, and now we need to find out the number of microstates. That is the number of possible arrangement for these electron configuration. Okay. Again we will apply the same formula. Now what we do is, whenever you have 2 orbitals mixed together, we have to put the formula separately. So basically for S orbital you will put the formula. So since it is the possibilities, right, S1 P1 possibility, so we multiply. So this is for S orbital and you multiply it by p orbital. That's all. So if I do it, you will be clear. Now see, first focus on the S orbital. Okay. Now for S orbital, here the maximum number of electrons that you can fill in the S orbital is 2, because it has only one orbital, and one orbital can have only 2 electrons. So basically for S orbital, the n value is 2. So 2 factorial divided by the number of electrons that are available here, which is 1. So 1 factorial multiplied by n minus r, so 2 minus 1 factorial. Okay. Now multiply this part with the p value. So in p value, the maximum number of electrons is 6 divided by r is the number of electrons occupied, so that is 1, n minus r, that is 6 minus 1 factorial. So if you solve this, you are going to get 2 factorial divided by 1 factorial multiplied by 6 factorial divided by 5 factorial. So this value is going to be 2 multiplied by, this one I can write it as 6 into 5 factorial divided by 5 factorial. So 5 factorial will get cancelled. So the total number of possibility is 6 into 2, that is 12. Okay. So for S1 P1 configuration, the total number of microstates is 12. That is the total number of arrangements that is possible is equal to 12. Okay. So this is the concept of microstates. Okay. So now we are going to move to the next topic, that is term symbols. So we have two things. One is term symbols, the other one is atomic term. So first we will see what is this term symbols. So basically, as I told you, microstates is the number of possible arrangement of a particular configuration. Now term symbols can actually help you in grouping the microstates of same energy into one term. So basically, when I say there is a P3 configuration, there are 20 possible arrangements. Now it is not necessary that all 20 possible arrangements have different energy. Some of them can have same energy. Some of them can say, for example, among these 20, 12 values have same energy. I am just telling an example. 4 values of second set of energy and the another 4 value of the next set of energy. So I can make them as energy 1, energy 2, energy 3. So basically these 12 arrangements which have the same energy can be collectively called as one term symbol. So grouping the microstates into a particular energy level is what we call it as term symbol. I hope it's clear. So grouping the microstates of same energy into one term. That is why we use the term symbol. So when we talk in terms of microstate, it becomes a larger number, right? 20 microstates. Sometimes you go for higher value, for example, D5, D10, D8, etc. The number of microstates would increase. So instead of speaking in terms of microstates, what we can do is we can speak in terms of term symbols, because certain set of microstates would have the same energy. So that energy level I can call it with one term. That term value we call it as term symbol. So it is generally represented by the formula 2s plus 1 Lj. Okay, so when we learn it, you will understand what the significance is. But first let me tell you what are these values. So basically here you can see three things. One is S, the other one is L, the other one is J. Basically S is the total spin quantum number, L is the total orbital quantum number, and J is the total angular momentum quantum number. So whenever you would have learned this concept that whenever an electron moves, the electron can make two types of motion. One is it can move around its own axis, other one is it can move around the orbital. So whenever there is an orbital motion, you have the orbital quantum number, and whenever there is a spin motion, you have the spin quantum number, that is S. And also this J term. So this J term arises because of something called as the spin orbit coupling. Whenever there is a spin orbit coupling, that results in the value of J. Okay. So basically we have formula to determine this L value, S value and J value. Now S is basically, the formula is S1 plus S2 modulus. You have to go up till S1 minus S2. So this is the formula. Okay. I will explain what it is. Again L value you will go from L1 plus L2 modulus up till L1 minus L2. And for J value, since it is J value is arising because of L and S, the formula is L plus S up till L minus S. Okay. Now it's very simple. You see here. Say for example, I have a configuration. So you need to find out these values and put it in the formula, then you will get the term symbol value. Okay. Now say I have a configuration 2p1, 3p1. Okay, this is a configuration and I need to find out the term symbol for this. So there are two things we find. First we will find out the term, then we will go for the term symbol. Now this is called as a term symbol. Okay, this is called as a term symbol. Now what do you mean by an atomic term? When we don't consider this coupling, the spin orbit coupling part, when we don't consider it, we simply write it as 2s plus 1l. So in those cases, we call it as an atomic term and we don't call it as a term symbol. The difference is this part, whenever you say there is a spin orbit coupling, you are bringing in the energy level into it. Okay, so this J denotes the energy level. So when you don't talk about it, you simply call it as atomic term, and when you talk about the energy level, you call it as the term symbol. That is the difference. Okay, so now you have 2p1 3p1 configuration. So it's going to look like this, right? You have 2p1 electron, 3p1 electron. Now what we need to do here is that we need to find out the term, atomic term. We are going to find out the atomic term for this. So what is the formula? For atomic term, the formula is 2s plus 1l. Okay. Now, first let us find out the S value. Okay. So for S value, as I told you, the formula is S1 plus S2 to S1 minus S2. See, you have two electrons here. These electrons only you denoted by the S value, right? If the electron is a spin up electron, you call it as plus half. Okay. And if the electron is spin down, you call it as minus half. So that is the value. Now here you see both the electrons are spin up. So S1 is plus half. This is S1. This is S2. And S2 is minus half. Sorry, S2 is also spin up. So S2 is also plus half. So the total S value is equal to modulus of half plus half. And you need to go all the way up till half minus half. So you need to keep reducing one value. So half plus half. The next one will be, now here there is no value in between. So directly we go up till, if you see here, then the next value would be half plus half minus 1, half plus half minus 2, etc. But here you see half plus half is 1, half minus half is 0. So there are only two possibilities. There is no value in between the two. Suppose there is any value in between the two, you keep putting those values. That is why we put this. So basically S1 plus S2, S1 plus S2 minus 1, S1 plus S2 minus 2, like that it keeps going on. Okay. So now we have found out the S value. The next thing that we do is we find out the L value. So for L value, the formula as I told you is L1 plus L2 up till L1 minus L2. So the configuration is 2p1 3p1, right? Now see, so we know that these orbitals have value, right? Azimuthal quantum number. What are the values? For p orbital it is plus 1, 0, minus 1. Again here also we have a p orbital, so plus 1, 0, minus 1. Now if it is a s orbital, the azimuthal quantum number is 0. For p orbital it is plus 1, 0, minus 1. This value is the L value. Okay. And for d orbital, we have 5 boxes. You start from plus 2 and you keep reducing one value, plus 2, plus 1, 0, minus 1 up till minus 2. And for f orbital, you will have 7 orbitals and you will start from plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. So this is a basic thing, right? So here the L1 value is plus 1 and L2 value is again plus 1. So what you need to do? Simply substitute it in the formula. So 1 plus 1 up till 1 minus 1. Again here in between there will be no values because you see 1 plus 1 is 2, 1 minus 1 is 0. I am sorry. So you need to reduce. So 2, 0. So between 2 and 0 you have 1. So 2, 1, 0. So there are 3 L values possible and there are 2 S values possible. So S value is 1, 0 and L value is 2, 1, 0. Now for these L values, we have specific atomic term symbols. Okay, what are the term symbols? So whenever you have L value 0, 1, 2, 3, we call it as S, P, D, F. Since it is a total orbital quantum number, we have to put it in capital. So there is a difference between this and this. Okay, this is the orbital value for this one particular orbital, that is L1 value is plus 1. So we put it in small letter. Now we are summation, we are doing a summation of this. So basically the summation is the total orbital quantum number. So we represent it by a capital L. So the same thing applies here, everything comes in capital. So 210, so L is equal to 210, which means L is equal to D, 1 means it is P and 0 means it is S. So these are the three terms that is possible. And the 2s plus 1, so as I told you, the atomic term formula is 2s plus 1 L. So L value we have found out, S value also we have. So what is the 2s plus 1 value? So if it is 1, 2 into 1 plus 1, which is going to give me 3, and if it is 0, 2 into 0 plus 1, which is going to give me 1. So basically there are two different 2s plus 1 values possible. Now, so if we have to sum up these things, what do we get? What are the atomic terms that are possible? So you have, one is a singlet. So we call this as a singlet. Okay. 2s plus 1, let us consider 2s plus 1 as 1. So singlet D, singlet P, singlet S. This is 1. Now let the 2s plus 1 be 3. So then it is going to be triplet D, triplet P, triplet S. So totally the number of atomic terms that are possible for this particular configuration is 6. There are totally 6 atomic terms that are possible, okay, for the configuration 2p1, 3p1. This is what we have arrived at, okay. Now atomic terms we have found out. Now what about the term symbol? Okay, once we know the atomic term, we can then find out the term symbol. So now we find out what is the term symbol. Okay. Now basically term symbol, what we do, the formula is 2s plus 1 L, that is the atomic term. We have to add the coupling part also, that is the J value. So take any particular term from here and we will find out the term symbol, because term symbol value depends on the term values, right? So let us take triplet D. Okay. For triplet D, if we have to find out the term symbol, now triplet D is the atomic term. Now what would be the term symbol for this? So basically here what is given is this atomic term is given. From here we can find out two things. One is the L value, the other one is S value. So we need the J value. J value is L plus S modulus up till L minus S. Okay. So here 2s plus 1 value is equal to 3. So this is 2s plus 1, right? So 2s is equal to 2. So S is equal to 1. So here S value is 1. And we know that if it is D, the L value is 2. So here L value is 2. So you just substitute it in the formula. So 2 plus 1 up till 2 minus 1. So 2 plus 1 is 3. 2 minus 1 is 1. So in between the two there is only one value, that is 2. So there are basically 3 terms that are possible, that is term symbols, triplet D3, triplet D2 and triplet D1. So basically we put this 3, 2 and 1 at the bottom. So triplet D is the atomic term. So triplet D3, triplet D2 and triplet D1, which are the 3 term symbols that are possible for this particular atomic term. So I hope it's clear. So basically there are two things. One is atomic term, other one is term symbol, the next one is the microstate. Okay, all three are interconnected and you should not have any confusion between the three. So basically you need to know what specifically is being asked in the question, whether they are asking you the atomic term, whether they are asking you the term symbol, and also they will have some questions wherein they mention you about the ground state, which we will also see in this particular part, in the next part. Now we will do some examples before going into the ground state term symbols. Okay. There is also one more possibility of question wherein they ask you find the number of microstates for, say for example, triplet D. Okay. So basically instead of giving you an electronic configuration, they give you an atomic term and ask you to find out the microstate. So microstate, we have learnt one formula, which is n factorial divided by r factorial into n minus r factorial. But this formula you can apply it only when they give you an electronic configuration. But instead of electronic configuration, if they straight away give you an atomic term and ask you to find out the microstate, you have a formula for that. That is 2s plus 1 into 2l plus 1. That's all. It's a simple formula. 2s plus 1 into 2l plus 1. So when do you apply this formula? When they give you directly an atomic term and ask you to find out the microstate. Okay. So basically for triplet D, the 2s plus 1 value we know from the top, right? Basically atomic term you need to know what it means. So 2s plus 1 L, and if the term symbol then there will be J. So 2s plus 1 is always denoted at the top. So basically the 2s plus 1 value is a direct value, so that is given as 3 multiplied by 12 plus 1. We know that L is equal to 0, 1, 2, 3 S, P, D, F. So here D, for which the L value is 2. So 2 into 2 plus 1, right? So basically you will have 3 into 5, which is equal to 15. So basically the number of microstates that are possible for triplet D is equal to 15. Okay, so this is the second type of question. For example, if they give you something like singlet G and they ask you to find out the number of microstates. So what do you do? So the top value is 2s plus 1. So 1 into 12 plus 1. So G value, so if it is 4 then it's going to be G, right? So 2 into 4 plus 1. So which is going to be 8 plus 1 9, 9 ones are 9. So the total number of microstates for singlet G is equal to 9. So there are two formulas. One is formula to find out the microstates from an atomic term. The other one is a formula to find out the microstates from this thing. So we will do one question now. Question is basically for P2 configuration. Let us find out three things. One is atomic term. Then we will also find out the term symbol. And then we will also find out the number of microstates. Okay. So we have this, then we will do the ground state term for the same question. Okay. So basically we have P2. So basically this is going to be P2. So the formula for atomic term is 2s plus 1 L, right? So what we need to do first is we need to find out the S value. So basically the S value is S1 plus S2 up till S1 minus S2, right? So here both the electrons are plus half. So half plus half, you go up till half minus half. So half plus half is 1, half minus half is 0. So there are two particular spin multiplicity values, 1, 0. Okay, so if it is 1, then 2s plus 1 value is going to be 3, and if it is 0, you substitute it here, then the 2s plus 1 value is going to be 1. So basically these are the two s values, and if you substitute that s value here, you are going to get 2s plus 1 values. So this we have found. Now come to the L value. So the L value is, you have to see here, plus 1, 0, minus 1. So L1 plus L2 up till L1 minus L2. So here L1 is 1 and L2, this is L1, this is L2. So L2 value is 0. So 1 plus 0 up till 1 minus 0. So which is nothing but 1, and 1 minus 0 is also 1. So there is only one L value possible. So whenever L is equal to 1, so whenever L is equal to 1, 0, 1, 2, 3, so S, P, D, F. So whenever L is equal to 1, it is P orbital. Okay, so the atomic term is going to be P. So what are the possibilities? So you just substitute here 2s plus 1 L. So 2s plus 1, there are two values. One is triplet, the other one is singlet. So triplet P is one atomic term, singlet P is the other atomic term. So there are two atomic terms possible. One is triplet P, the other one is singlet P. Now going to the, so these are the atomic terms. Now coming to the term symbol. So when we talk about term symbol, the formula is 2s plus 1 L. You also have to include this J value. So for these two atomic terms, we find out the J value. So J is nothing but L plus S up till L minus S. Okay. So first L value is 1 only and S value is 0. This is one case. The second case, L value is 1, S value is again 1. So there are two possibilities of S value. One is 0, one is 1. Okay. So L plus S. So 1 plus 0 to 1 minus 0. So that is going to give you only 1. Okay. The second case, 1 plus 1 to 1 minus 1. So that is going to give you 2, 1, 0. Because 1 plus 1 is 2, 1 minus 1 is 0. So it's going to be 2, 1 and 0. So what are the possibilities now for the atomic term symbol? So the atomic term symbol now becomes, see, for triplet P, that is when this is basically 2s plus 1 is equal to 3, right? And this is 2s plus 1 is equal to 1. So first I am telling for this. So this triplet P, there are 3 possibilities. So triplet P2, triplet P1, triplet P0. The next is singlet P. So this is the singlet P part, right? So singlet P, there is only one possibility, that is singlet P1. So total number of atomic term symbols that is possible is equal to 4. The total number of term symbols possible is 4. The total number of terms is 2. Now we consider the microstate. So the microstate, the formula is n factorial divided by r factorial into n minus r factorial. So the configuration that was given to us is P2, right? So the maximum number of electrons is 6. The number of electrons filled is 2. 6 minus 2 factorial. So this is going to be 6 factorial divided by 2 factorial into 4 factorial. So you can write it as 4 factorial gets cancelled. 2 3s are 6. 5 3s are 15. So the number of microstates that are possible is 15. Now the one more thing that you need to know is, if you find out the microstates from these two, okay, that part you can do it on your own, because whenever there is a configuration given and when you find out the microstate, the formula is 2s plus 1 into 2l plus 1, right? So if you find out the microstate for this part and for this part and add it together, then also you will get the same value 15, which you can check it for yourself, okay? That would be an assignment. So triplet P the microstate, and also for singlet P the microstate, you find out. Whatever value you get, you add the two, then again you will going to get the same value, because both are same. For P2 is the configuration, these are the atomic terms of that configuration. So I hope this part is clear. Now the last part that we have in this atomic term, term symbol, etc. is identifying the ground state term. Okay. We have a formula, basically it's the Hund's, basically for electronic configuration we find out the ground state using Hund's rule, right? The same formula applies here. We have Hund's rule of maximum multiplicity, which we use to determine the ground state, because generally in exams they ask you the ground state term symbol, okay? Because see, for this P2 configuration there are 2 terms possible and 4 term symbols possible, but we need to know which is the ground state among these, okay? That means these are all, as I told you, atomic term symbol as basically denotes the energy levels. So basically there are 4 energy levels in which the electrons can be arranged, but which is the actual ground state, that is the lowest energy level value among the 4, that we need to know, okay? For which we apply this rule. The rules is very simple. The first point that you need to consider is the S value, okay? The spectroscopic term with highest spin multiplicity will be the ground state. Now what do you mean by highest spin multiplicity? Maximum 2s plus 1 value. The 2s plus 1 value needs to be maximum, okay? That means there should be maximum number of electrons in it, unpaired electrons in it. So basically spin multiplicity arises from the unpaired electron. So if you have maximum number of unpaired electron, the 2s plus 1 value is going to be higher, because the S value depends on the number of unpaired electrons. So that will be the ground state, okay? Now you come to this part, okay? For this we will find out. So we found out for this P2 configuration, we found out 4 atomic term symbols, right? The 4 atomic term symbols, I write it over here. The 4 atomic term symbols are triplet P2, triplet P1, triplet P0, and then you also have singlet P1. So now among these four, we will try to find out which is the ground state. So the first rule states that the highest spin multiplicity value, that is you have to see this top value. Now if you see here, this is the lowest singlet, so this is not the ground state. So among these three only any one is ground state. Now if in this such a case where two terms are having the same highest value of spin multiplicity, then what we do? Then we go for the second part of the rule. If two terms have same highest value of spin, then we check the L value. So the highest L value is ground state. So now you see here, let us now filter out. So this part already we filtered out because this is having the lowest spin value. Now you see here the L value. So the L value again you see P, P, P. All three are having the same L value. That is L is equal to 1, L is equal to 1, L is equal to 1. So in this case we are not even able to make out with the L value. Suppose you have this part triplet P, triplet F for example. Okay. Now when you have triplet P, triplet F, now here L value is 1, here L value is 3. So the highest L value will always be the ground state. Okay, but here that part cannot be applied. Now then what you do? If the L value is also same, then what you do? If two terms have same high L value, then you consider the J value. Okay, J is equal to L minus S will be ground state. Okay, J is equal to L minus S will be ground state, but there is a criteria for that. L minus S will be ground state if the orbital is less than half filled. Okay, and J is equal to L plus S will be ground state if greater than half filled. That's all. So now you apply this and see. So you had three terms, right? Triplet P2, triplet P1, triplet P0, and then singlet P1. Right? Basically this is out. So among these three we need to decide, but here if you see all the three are having the same S value and same L value. Now what you do is you find out the J value. So the J value, if it is less than half filled, so we found what is the configuration here? P2. P2 is basically less than half filled. So whenever you have an orbital in which there is a less than half filled configuration, you use the formula L minus S. J value is equal to L minus S. So here for P2, the S value is equal to 1, right? Triplet, triplet, triplet. S value is 1 and L value is now equal to 1. So L minus S, that is 1 minus 1, which is equal to 0. So J is equal to L minus S is going to be the ground state, which means triplet P0 is the ground state configuration. Okay, I hope it's clear now. So whenever you have such a this thing wherein same S value, same L value, then we consider the J value. So generally in questions what they do is they will ask you to calculate the ground state term symbol for any configuration. For example, let me do a question. Calculate ground state term for, I will give three questions. So one I will solve, the other two you can solve it on your own. Okay, so we are having four parts here wherein they have given you some elements and they are asking you to find out the ground state term. So basically what do you do? You first need to find out the configuration. So vanadium 3 plus, so vanadium is D3S2, so 3 plus means it is going to be D2. Okay, vanadium is basically D2 configuration. So you put it in the D2 configuration. Okay, and then you try to find out the ground state. See, they are asking you directly the ground state term. Okay, for ground state term, there is also a simple trick. So basically, whatever the configuration that you have, okay, now you see it is D2, right? So there are basically two unpaired electrons here. Okay, two unpaired electrons, which means the maximum spin multiplicity value is going to be 3 for the ground state. Okay, since they are asking the ground state, we can directly do. But if they are asking you all the terms, then you have to apply this formula, S1 plus S2 to S1 minus S2, if they are asking you all the terms. But since they are specifically asking the ground state, the spin multiplicity value is going to be maximum, which means the two unpaired electrons, the number of unpaired electrons, whatever the value is there, you just add 1 to that. So since there are two unpaired electrons, the 2s plus 1 value will be 3. Now if you have D3, then the 2s plus 1 value is 4, that is quadret. If it is D4, the 2s plus 1 value will be 5, that is quintet. If it is a D5 configuration, the 2s plus 1 value will be 6, that is sextet. Okay, so it depends on the number of unpaired electrons. You just need to add a plus 1 to it. Okay, so now since here there are two unpaired electrons, the 2s plus 1 value we can find it directly as 3. And then the L value. So here this is plus 2, this is plus 1. So 2 plus 1, 3. Right. So basically the maximum value only we take. So 2 plus 1. See, since it's ground state term, you need this highest, and L value is less than half filled means L minus S, greater than half filled means L plus S. So since it is the ground state, you take the maximum value. So the maximum value of spin is 3. The maximum value of L is equal to 2 plus 1, which is equal to 3. If it is 3, it is going to be 0, 1, 2, 3, S, P, D, F. So F. So the term is triplet F. And we also need to find out the J value, because they are asking us ground state term symbol. Okay, if it is ground state term, then this is correct. But if they ask you ground state term symbol, you also need to find the J value. Now see, this is a less than half filled, right? Then the formula is going to be L minus S. If greater than half filled, it's going to be L plus S. So L value is 3 and S value, 2s plus 1 is 3. So 2s is equal to 2. So S is equal to 1. So 3 minus 1, so which is going to be 2. So the ground state term for vanadium 3 plus triplet F2. So I hope this part is clear. You can try to do these questions. In the next part of the video, I'll try to cover the ground state term symbol for diatomic molecules. Okay, that time I'll tell you the answers for these questions as well. I hope the video was helpful. Thank you.